Then told me that this to make the random state.
Oh, yeah, we need to start.
Yeah. So today we have to have Kun Cheng, and for Kun, this is PhD. He graduated in 2024 from Technical University, and then he joined Pittsburgh. His first postdoc, but now he's gonna tell us about quantum state tomography colliders.
Okay. Thank you for the introduction, and thanks Jen for the invitation. Although he told me he was going to be late, but I spoiled part of my talk to him already, so I can start. I think I can start without him. So the title of my talk is quantum state tomography. This is one fundamental procedure for quantum information study at colliders. As we know, recently there are many works on the quantum information study at colliders. So I hope that in this talk I can convey the basic picture of what everyone is doing right now. Okay, so let me begin my introduction with I think it's a very interesting story happened at the LHC. As we know, the way we understand the microscopic work is based on quantum mechanics. But interestingly, like 20 years ago or even earlier, we didn't think of many things in this way. We didn't think to measure the quantum information. Recently, now there are more and more. One important reason is with the help of experimental techniques, more and more people are thinking along this line to think about measuring quantum information at collider and find that our high energy collider is a really compelling environment to measure these things. So the first experimental result is from Atlas, the measurement observation of entangled top quark near threshold. So this figure is the Atlas result. The y-axis is some measurement of entanglement I will introduce later. The x-axis is the free mass beam. This is very near threshold. This is slightly higher energy. So below this gray line means the entangled, above means separable. So you can see a clear, the black dot is their mirror data. You can see a clear signal of entanglement. It's very entangled than this classical bond. In addition to this fundamental measurement, of course, it's the highest energy we achieve is interesting. Another thing is that this TD bar near threshold is measured to be more entangled than our theory expectation. So later on, CMS repeated the measurement and confirmed this result. So this one is without just a normal theory calculation. You can see the measurement result is more entangled than the theory expectation. Then they add a pseudoscalar near the boundary. They find that after adding that, they can explain this discrepancy. So in the next publication, they use this entanglement measurable. They use this measurable used in here, and they focus on the discovery potential, focus on the cross-section, and they reported cross-section of they didn't put the volume in the paper, the pseudoscalar axis, like 8 picobar. So I think this is a very interesting timeline to show how this observable we use in this quantum information can help us with understanding the physics slightly better. Okay, so in this talk, the topic I'm going to introduce is the slightly more basic, also slightly more general procedure, the procedure to reconstruct the whole quantum state. After we have the quantum state, of course, we can ask the entanglement or whatever for either quantum information side or for our high energy side. After we have the complete state, this is the best information we can get. So I will first introduce some basic concepts, then introduce the quantum tomography for spin state and the flavor state. So let me start from some basic concepts. Although the main topic is tomography, I will also introduce some more specific quantum information observable like spin correlation and entanglement in case some of us are interested in this one or two observables. So let's say we have two particles, two spin half particle or two qubits, and their spin can be correlated with each other. There are many different ways we characterize their spin correlation. The simplest one is just the first one. We put a spin measurement on each of them and their correlation, just a classical correlation. This is the simplest one. It's non-zero, there is some correlation. And we can also ask this question in a more quantum way. This is how we define entanglement. We want to see these two state vectors, whether these two state vectors can be written in this separable form or not. If it is separable, then of course there's no entanglement. We do a measurement on particle A, we don't change anything about particle B, or we can make it slightly general to this is pure state, this is mixed state, this is the definition of separable. So entanglement is defined as non-separable. If there's no way to, we can do any kind of decomposition once, no way to write in this form, then it's entangled. Okay, another famous criterion, another famous measurement of the quantum correlation is the Bell inequality. This actually asks for a more specific question whether the system, the measurement outcome can be described by a local hidden variable or not. Let's say Alice measures the spin of particle A, Bob measures spin of particle B. Assume that there is a hidden variable lambda control their measurement using a classical probability.
Do this theory make any sense?
It's of course now we don't think it makes sense.
What do you think?
I don't think it makes much sense.
Say that then.
Because now we understand the feeling, we know quantum mechanics is correct.
We'd like to check
Yes.
quantum mechanics. We check the Bell's inequalities
Yes.
For, I don't know, 70 sigma, and there is no difference whether we check it for 10 sigma or 70 sigma.
Yes.
Absolutely no information in that.
Yeah, so we know quantum information is correct, and we can.
But is such a thing as, is there a consistent theory of hidden variables? And my claim is probably no, right? But I'd like to know if you know more, right?
So this is one subset we can exclude from measurement. Like this one.
Cannot even say what that is, right? So
Yes. You can always assume a superdeterminism. There is something control everything, even non-local interaction. Then that one is no excludable, but usually we don't discuss the theory that cannot be excluded, right?
But you're still assuming that the theory is linear?
No, this is just means the outcome of measurement is described as classical probability. That's assumption.
Yeah, but you're still assuming the theory is linear, right? You can add amplitudes together.
Not amplitude, but a classical probability. Add classical probability together.
The statement, but
Yeah, it's not about the system.
I see. So you can actually also test nonlinear quantum mechanics?
This is a different story. Nonlinear
But
quantum.
it's the same. So
Uh-huh.
you think you'd be able to, so if you had a nonlinear modification of quantum mechanics,
Yes.
can you test it or not?
No, this inequality cannot test the nonlinear one, because this is only test for local hidden variable. If we see the violation of Bell inequality, we can exclude the local hidden variable. But quantum mechanics, nonlinear quantum mechanics can both violate this one.
that's local quantum hidden variable, whatever. Does it carry energy?
Where
If I, like whatever the variables we have in physics, right? We
Yeah.
change them, they carry some, we participate in the interactions, carry energy and so on. If I change something very quickly in time, the energy changes always, right? So this
so from my understanding, hidden variable is not to describe the interaction, it's more describe the measurement outcome. Energy, of course, is one measurement. We can measure the energy of two particles. If the energy is described by hidden variable, we still use the same this kind of formula. to
So
describe.
is this some sort of a quantum number or not?
No,
No.
it is quantized, for example, the spin plus or minus. Yeah, it is quantized.
So if
But-
I have a.
But we don't
if
need
I
a
have
wave function.
State.
Yeah.
Like that, and I have an extra degree of freedom with lambda, right?
Yes.
Would I describe the standard sort of heat capacity, so capacity of like Planckian distribution as two, but the two spins, right? It's like if the fact that I have lambda, how you cannot change the number of states.
can I maybe say, because
Yeah.
like this is a very general theorem, okay, and all it says is I have like two coin tosses, okay? And the question is, if it is true that it is possible to simultaneously know, so the coin tosses are, think like they're non-commuting measurements, okay? And if it is possible to simultaneously know, the outcome of both, so that I can measure B and without destroying information about A, okay, you can put bounds on the set of measurement outcomes that are classically possible. And then quantum mechanics violates those bounds. So like, it's really, there's really no assumptions being made about like what these hidden variables are. It's really just that there's some, that everything, that all of the information exists at the same time.
Sure, I know that. I just wanna know that is there anything more serious than just saying hidden variable? Then I like let me entertain it as an actual opposition to quantum mechanics. Then I want to know what this thing is, right? How I should be treating it. Does it carry energy and so on? No, or does it count as an actual extra state of matter, right? Like before atomic physics, we didn't know electrons had spins, right? But later we discovered, right? So it's just it's not a serious physics. That's what I'm trying to say.
Okay. Using the other problems with hidden variable theories besides Bell inequality.
Yeah,
Right. I mean, like
the violation of this melancholy implied could it possibly be nonlinear quantum mechanics or not?
I mean, you need this thing called like contextuality, where which really is something where you have like non-commuting measurements in order to violate this.
I mean,
nonlinear quantum mechanics also have
for a
some.
second,
no.
for a second, I forget about all these issues with causality and so on, right? If it's a good question. Like if I slap in psi cube term, which is gonna be what is it called, Gross-Pitayevsky equation or something like that, with an arbitrary small coefficient, right? Would this lead to this? I doubt it would probably create some correlations at a higher frequencies. Like it sounds like a higher harmonics or something like that. So, but like if it's part of Schrödinger equation, I say like, and it's adjustable, right? I can always make it smaller. So I suppose you can possibly set constraints from Bell inequalities on this, but it's not going to be like super tight constraints. I don't know.
It also depends on the level of quantum system. This one is designed for qubit, the simplest one. The one you mentioned, I believe, is a higher dimensional infinity dimension one. Okay, so for yeah. So yeah, we can discuss Bell infinity later. There are many to discuss. Okay, so this is the definition. This is just definition. Let me write down explicit criterion for how do we measure it, especially how it has measured the result. For entanglement, whether we can write symmetries in this form or not, for qubit system, we can use one single variable to describe it. This is the so-called concurrence, define some manipulation with the matrix, the slightly complicated. If it is 0, it means separable. If it is 1, it's maximally entangled. It's increasingly, it's just proportional. It's larger the concurrence is, the more entangled it is. So
lambdas are is it like squared is lambda?
Lambda is the eigenvalue of this matrix. Yeah. Okay, this is complicated, but in calligraphy, when we produce an unpolarized state, like TT bar production, usually we can have some simpler analytical form like this one. If the state is close to a spin signal, it don't have to be a spin signal, just a spin configuration is slightly close to it. Then the concurrent have a very simple form. This trace C is a correlation matrix CID. And this is basically the observable at a CMS reconstructed to observe the entanglement. And for Bell inequality, the criterion is actually simpler because the definition itself is from measurement. So A1, B1 spin measurement along some direction. Let's say this is along A direction, B direction. No matter which direction we choose, as long as we can find a set of directions for direction, make this inequality is violated, this larger than 2 is violation. Make this larger than 2, then this Bell inequality violation. So we can choose whatever direction we want, like we can choose some simple direction. We fix some coordinate X and Y direction, then we have a linear combination in some certain entries in the spin correlation matrix. This indicate Bell equilibrium violation, or we can try to optimize this kind of the possibility. So in my talk, I will just use the simple one as an example because this is linear, is more easy to relate to collider observables. Okay, so
Maybe you can explain to us what does concurrence mean in the slide number 6.
Concurrence is a quantitative measure of entanglement. Entanglement is simply definition, whether it is separable or not. But this definition is hard to quantify, right? So it's just a quantified measure.
And first, I can have many measure of that.
Yes, this is
actually measure something.
So that is why I restrict to qubit pair. For qubit pair, this one is the necessary and sufficient condition. This is the simplest one. But for, let's say we do WW boson qubit pair, then we don't have a necessary sufficient condition. We only have a necessary condition.
So if I apply the already known example of entanglement, such as the epsilon 4s gave to B0, 0 bar.
Yes.
This quantity is what, 1?
Yes, this is B bar minus B bar B is maximum entangled. It's a singlet state. So. Okay, so in addition to this entanglement and Bell equilibrium violation, these two are trying to characterize quantum correlation. There are many other quantum information variables, but for TD bar, there are many already studied. Like Discord describes the mutual information between two particles, the difference between classical mutual information and quantum mutual information. Quantum magic characterizes the computational advantage of quantum computer over classical computer on this system. So if it is larger, then this system is more suitable to be computed at quantum computer. There are many information we can study. So the point is, as long if we want to study this information, firstly, we need to know what the quantum state look like. So this is basically. Oh, this is the phase space. Sorry, I didn't produce. This is just an illustration of this top quark pair production phase space. This is scattering angle and energy.
Performance of these different entanglement measures on the same phase space.
On different phase space, this is control plot on the phase space. Different scattering angle, different energy.
Like showing the same phase.
Yeah, same phase space region, but different.
On the left appears to be more sensitive.
Some of these observers are trying to ask different questions. So quantum entanglement simply ask the question: the density matrix is separable or not? This is a question we just showed earlier. These two are different questions. For example, the magic want to ask the computational advantage, whether this system is suitable to be computed in classic or not. Yes, they are somehow independent. No. They are kind of independent. They just serve different purpose, completely different purpose. Yeah. In terms of quantum correlation, entanglement, Bell equilibrium, they have a hierarchy. When someone is stronger, someone is weaker. But these two are different. All right. So let's go to tomography. The procedure we want to reconstruct the complete quantum state because the one or two observer cannot uniquely identify it. As for example, entanglement, we can have maximum entanglement like BB bar minus B bar B or plus B bar B or some size. They are all maximum entangled. Okay. So if we want to uniquely identify the state, what we need to do is a complementary set of measurement. For one particle system, let's just for qubit, one qubit, we need 3 operators, basically 3 Pauli operators, because we know the density matrix can be expanded in the block vector space described by 3 real coefficients. And for 2 qubit, it is similar. The complementary measurement means 3 operators on each side of the qubit and the correlation as a 3 by 3 correlation. So now we will need 15 parameters, 15 operators to achieve the complementary. And after we have the density matrix, of course, we have the complete information, whatever we want to study, we can do it either for quantum information or high energy theory. So I will introduce two parts. First is the spin state, another part is the flavor state. Okay, for spin state, I will just introduce spin half particles. For spin one, it's a very simple generalization, but much more tedious. So, okay. So for spin state, in collider experiment, firstly, we encounter one difficulty because we don't have this Pauli operator measurement directly. For example, we don't have a polarizer installed on detector. This is one thing. Another thing is some particle like top quark, they decay before reach the detector. So we never have a direct measurement of this thing. So we always need some indirect infer or assumptions. We need theory inputs on it. There are different ways to put our theory inputs, either in the production part or the decay later on decay part. For the production part, let's assume that we can uniquely identify the production mechanism. Let's say we are 100% sure we have a Fermi pair decayed from a scalar or a pseudoscalar. Then just from quantum number conservation, we already know the spin state, the spin correlation matrix will look like this. This is a spin singlet, these other spin triplet. For vector boson, let's say Z boson decay. If we know it's vector, we have some additional kinematic dependence, scattering angle dependence, so it X is some kind of negative. But anyway, it's basically in this form. So this would simplify our reconstruction a lot. However, in some cases, if we don't know the production kinematics or if we are unable to reconstruct it, so it is still possible to reconstruct whole spin state, like from the decay, especially for top quark, because in top quark decay products, its spin information is carried by the final state. And this can also be generalized to the fragmentation of quarks later on. So these two are slightly more complicated, so I will introduce I will focus on decay approach in the later part of my talk. The key point to reconstruct spin from decay is priority violation. Just as how we observe priority violation in the very beginning, we have a polarized mother particle. We see that the daughter particle have some spatial prefer to align with its spin. Then we see the priority violation. And on the other hand, if we assume we have a top quark with spin vector B along some direction, we do some calculation, we can see that the average direction in top quark reference of its decay lepton is basically its spin vector. We have a very elegant form. There is the normalized 3 vector of the lepton, so the average, this is basically average direction, give us the spin vector. And for TT bar pair, this is easy generalization. Just this lepton decay from top, this lepton decay from anti-top, so they reconstruct their polarization vector respectively, and they are putting them together. Their correlation gave us this 999 spin correlation matrix. So lepton non-decay is just one mode. We can use many different modes like harmonic decay or whatever kind of decay, or even other spin half particle like tau lepton, lambda hadron, or the others.
Sorry, I got confused. Top
Yes.
decays to B and the double, and then you ask the W to decay to lepton? Or?
Yes, also W decay to lepton.
It's kind of like direction, so that kind of carries some.
Yeah, so they'll carry some for the mother particle or mother particle.
And just like naive, but yeah, if I was doing this with photons, right, and I want to know how, like, there's some question of, how long, what's the coherence time of the photon, right? So they, initially they're created in a Bell state, say.
Yes.
Spin singlets, but now they're propagating away from each other, and then, obviously, if they propagate far enough that they're interacting with other stuff before they hit
Yes.
the detector, then you're not going to get good information about what that initial state was. So is it known, like in the what's the coherence length of these spins or whatever in these?
In vacuum, I think that is small. In material, I have no idea how long it is. In vacuum,
Is that at the LHC with your detector? Like, is it?
Okay, that is
known? Like how far these guys?
that can be computed. Yeah,
These things occur at the interaction point.
Yeah.
They don't leave long enough to actually even exit the pipe. So it occurs right there, right? At one.
It's in the back.
Yeah, no.
They assume the top part decay is already, once it decays, it's going from.
Yeah, that's being already transferred to its decay part. Even for slightly long-lived particle like tau lepton, it's just radiated maybe some soft photons, but this dilution effect is very small. Yeah.
That's,
The
stable part of the electrons and gluons.
And you were saying that there's not processes that can sort of change the spin angular momentum after the decay. Like, you know, like say I decide to measure an SZ or something like this, like.
Measure what?
Well, like if it's really a spin and a half particle, you know, what I want to do is I want to do coincidence measurements of the two particles, you know, along different spin axes, right? So I really need to know that there's nothing between where the decay happens or I would like to know that it's unlikely that something's going to happen between
Trouble
decay and the detector.
is that you cannot measure speed very well.
Right. I understand that this is all indirect, but like, you know, it's like, well, what if at some point a photon came in and did something?
It's
you know?
this parity violation that helps, because you have the distribution of the products, the angular distribution, carries the information about the initial spin.
So it would need to get
It's a
knocked
magic
off.
of parity violation.
It would need to get knocked off course, basically.
Right, so the statement is that you follow the angular distributions of particles, unstable particles really well, and you know that it comes from the interaction that correlates these directions with the initial spin, and you have some information.
And there's good information that you don't see missing momentum, so these guys are not getting like kicked around by random.
Yeah, so this momentum change is quite small.
Yeah.
Yeah. Okay. So regarding your question, it's actually quite related to later on some experimental difficulties, because finally the distribution will be smeared, but we are able to reconstruct. I will introduce in the next slide. So yes.
So the spin of the function collects the decay, and is that your setup?
No, it's hard to say, because in principle, after a spin half particle decay, the decay final state is still a wave function, a superposition of different plane waves.
Yeah.
Right.
So this is this robust.
So these two setups, if you really calculate, they have the same observable. So in principle, we cannot distinguish where we collapse the wave function in our primary setting.
Covariance happen.
Yeah, so this is the thing we cannot measure yet. So it can happen like as a decay, or when the decay final state reaches there is no observable to distinguish these two assumptions. So that's why we don't need these two assumptions, and with the observable the same.
So if I think about the peak bar production out of quarks or gluons inside the colliding two protons, right? And then they decay almost really immediately on the hadronic scales. Still have some interactions of quarks, the residual quarks that were there in the protons with this the particles that come out of.
Yes,
So there is some in there. It's not going to be a large.
I think this one is hard to.
But it's more than what you possibly see like detector.
Yes. Yeah, what the effect you just said is hard to compute. People have computed the other effect, like just the radiation of photon and the error correction. These can be slightly easier to compute, and it's basically 10% change, something like that.
Well, if I just do a naive picture, right, all of that, the T-bar production and the decay, all happens within the cloud of other spectators.
Yes.
Right? That in principle have strong interactions, right? So that's a question.
Yes, I think
how far this can travel, and
yeah, I think they do calculate this thing.
okay.
They do calculate in the decay, like top part decay to, let's say there's a big part. When they calculate the NRO correction, they include the big part interaction, QCD interaction with the others, they include some others. So I think they partly answer your question. Okay. So after introducing this spin analyzing power, it's just a factor, might dilute our reconstruction a little bit depending. One is the maximum, then it can be slightly smaller. But we still have this elegant formula of the reconstruction. Still, this 15 parameter reconstruction can be very easily. Okay, in reality, of course, it's slightly difficult. That is why people haven't do it until very recently, because there are some experimental challenges, especially in the true distribution, we have detector smearing, and in the leptonic decay, we have missing neutrino. We have a two-fold solution. We cannot even solve it event by event. So the detector distribution would look completely different from the true distribution, especially for semi-leptonic decay. So in that case, trying to unfolding from the detected one to the true one is kind of magic, but there are many papers working on it, many theory papers, including both experiment paper, and it's quite amazing that they can do it really, really well. They compare the reconstructed pattern level distribution, looks perfectly same. So in this talk, I'm not going to introduce this. It's too technical, but I think this is very important to see the overall picture. Okay, there are also some other subtleties like the basis dependence. If we didn't choose the correct basis, when we average all the events, we can cancel all these correlations. And there are high order corrections. Luckily for top quark and all the other high order correction is still safe. Our qubit description is still safe because it is still factorizable. However, in some cases like this W boson, in this case, there are some non-factorizable diagrams. In that case, the inference will just make our qubit two spin particle description invalid. So in that case, should be a more careful treatment. But for our case, that's just some percentage change. Okay, so after introducing this experimental subtlety, the overall reconstruction procedure will look like this. Firstly, we don't assume what the initial state is. We want a general reconstruction, general parameterization. We have this 15 parameter parameterization, and using the decay amplitude here, we put it on the spin density matrix here. Then we can write the final state differential distribution of a 15 parameter distribution. And of course, we can add a smearing effect, experimental effect on this distribution. And we have a template. We fit this template to the measured result, measured distribution, and we extract this 15 parameter. That is the overall procedure. And Atlas and CBI are already doing this whole 15 parameter reconstruction. Okay. And in addition to this complete tomography, if we are interested in one or two specific observables, it's much simpler, like the entanglement. The entanglement, the concurrence, as we mentioned earlier, is related to this trace of correlation matrix. And this one can be reconstructed from a single observable, the angle between two decay leptons. So we only need to look at one-dimensional distribution, not this big distribution. And for Bell equilibrium variation, it's also simpler because here, if we use the simpler version, the linear version, so this one is just related to the azimuthal angle correlation between two decay. We only need to look at also two-dimensional distribution. We can reconstruct this one. So partial distribution give us partial information in the density matrix. Sometimes if you are interested, it's also quite interesting. Okay, now let me go to the last piece of spin half particles, quarks. Quark is similar to, it's not similar to top quark, but it's also unstable particle. It never reached the detector. We cannot detect them. However, its spin is still well defined. As long as the factorization theorem holds, we can still have a pattern level spin state or pattern level thing of the quark pair. And the question is whether we can extract the spin state. So this would be different from the decay because here it is a priority conserving process. So our previous discussion is not quite valid. We need some different Lorentz structures.
Sorry.
Yes, light quarks. Yeah. So, so I going to consider this process, finding, like say at 10 dBl, we find a pair of pion in quark final state, a pair of pion in another quark final state. Let's see if we can reconstruct the spin of the quark. Firstly, let's define the spin density matrix, just like the top quark pair. Let's compare it with the decay. In the top quark pair, the width is narrow, so we can factorize it out. So we have a production part, decay part, and everything is well defined. for this QQ bar production, as long as factorization home, of course, this is assumption. This part we have to admit this assumption factorization 0. Then we can still factorize it as production and fractionation. Now we have a well-defined pattern level density matrix here to study with, and we have the fractionation function of quark going to a pair of time, finding a pair of time in yes. So
So there is some property of the fragmentation. I cannot require the fragmentation to preserve my spin information without some washing out.
yes,
What's the property we have here from theory?
I'm going to introduce it right now. Yeah, so the difference between the decay is that for the decay, we have this parity violation. So we can write down a Lorentz structure like a momentum dot spin vector in the three momentum, three spin. Okay, but here, there's no way we can write down this. So this structure of the density matrix would look completely different. Let's keep this in mind and try to decompose the structure. We can see the first piece we can write down, of course, the trace is the overall probability of quark go to a pair of pion. The second piece is the longitudinal part, and we'll see that at leading order, there's no way we can write down a legal parity conserving structure here. So this part have to be 0. This is different between spin part. And for the transverse part, however, we are able to write down a Levi-Civitz tensor. This is on the Levi-Civitz tensor defined on the transverse plane. And this is just some normalization factor of the momentum. And we are left with a scalar function. So basically, this density matrix is described by two scalar functions. One is the unpolarized fractionation function. One this is called interference dihedral fractionation function. This describes the transverse spin relation with the final state distribution. So these two different ways of decay cannot be calculated perturbatively. So there is no any theory input on it, but we can fit it from experimental data, just like PDF, just like how we extract PDF. Both have already been measured, observed, measured, and to a good precision from experimental data. So basically, Jefferson Lab is the only group that is working on this. And so, yeah.
There is a hybridization function taking you from one quark state, which is the color state, to a pair of color neutral state. That's what you're assuming. How to factorize into
This function is not amplitude, because amplitude level, what you said, of course, is not valid. Yeah, this is the probability level. This one is already, it's like the square of the splitting and hybridization amplitude. Of course, the amplitude we cannot compute. This is just a most general parameterization.
Sorry, this may not be the most general one, right? The most general one, let's say I decide to write it as the density matrix of the quarks, right? This a pair of quarks we're going to map onto the 4 pion final state.
Yes.
That will be the 2 to 4 transition matrix. Here you factorize that into a product 2 matrix.
Yes. So first of all, pi don't have spin. That's why I choose pi. That's why it's slightly easier. And also I assume that here if we integrate over the total transverse momentum of pi plus pi minus, only look at the relative difference. This is the most general one. This is the most general 4-particle phase space. Just all the phase space kinematics are already here.
But right here, then you discuss about some spin projections. That it sounds like you know more theory about what's going on.
Yeah, no one knows what is going on. So this is just from symmetry argument, from Lorentz symmetry. This is the only thing we can write down. And experimentally, we have measured this is non-zero. This is the story, like the PDF.
That's an assumption.
Yeah, this assumption is a factorization theorem. That's the assumption. Yeah, we all admit that's assumption.
Right. Double factorization. One is factorization into the quark system into quark, then factorize the hybridization product is also factorized.
This is just a normal factorization, right? So this is pattern level starting. This is a quark go to hadron. Just a normal factorization. Okay, so
you trying to
extract information about original
Pattern
Q
level.
and Q bars,
Yes.
right? That give further rise to the jet, right?
Yes, from the hadron final state.
Right.
Okay. But we look at a slightly low energy, so it's an exclusive measurement, semi-inclusive. Semi-inclusive. Some are. There can be some. We have to only 4 pion, no additional pion, but there can be something else. Something else. What that is fine. Like pi 0 is fine. Or the other thing is fine. Yeah, other hadrons. Yeah, subspace. But this is. Yeah.
It's known that if you create some hyperons, the strange work they somehow transverse the polarized thermal pendulum. It's just I cannot explain it. It's an empirical fact.
Yes, that's
been
one.
used,
Yes.
In thermal absence.
Yes. Yes, that is another effect similar to this one. Okay, so now we have some kind of form of the function. We can input this back to this formalism, go to the parameterization, write down just plug in the density parameterization, and we can hope to get a distribution just like the decay one, this one. So for simplicity, let's just focus on the transverse part, just focus on this azimuthal angle distribution. We can compare this. The first line is the decay part. The second line is the polarization part. You can see the basically the same. So the only difference is that this big block is the non-perturbative functions. We need to take them out, and we don't know how to calculate them. And another sorry. Another slight difference is this structure. Here is plus sign and minus sign. This is because in the decay part of the final state tend to align with the spin, but here, let's say we have Parkin here, the difference, momentum difference between 2 pions tends to be perpendicular to the transverse spin. So this is just from the structure we wrote down. Okay, now with this one, we are able to extract some quantum information. Such as we define this one is the Bell included variable. We can see this is directly this azimuthal angle asymmetry, and some kind of non-perturbative spin analyzing power. And we define this big block as a factor alpha. Then luckily, all of these factors are available, publicly available. The usage of these are very similar to PDF, and they have a scale, have a kinematics, and they give us some results. So these are fitted from some additional complementary process, like a BIS process, like some other process. Okay, for this one, for the azimuthal asymmetry, we also have existing data. So now we can basically look at the quantum information with existing data at 10 GeV Bell. We take this data from Bell paper. We take this analyzing power from from Jefferson lab, and this dotted line shows the experimental dot. The solid line is the spin analyzing power alpha, and the ratio is the thing we want to study. This is the quantum information observable, the Bell increase observable we find. In their original data, they didn't add a cut. We add some additional selection cut cosine to select the central region. We can see there's a clear signal of Bell increase violation. This is because for E plus minus Q bar process, it is easier to select a pure Bell state. This process just QED process. It is so simple. In the central region, it's maximally entangled when cosine theta equal to 0. If we put some cut, like a cosine smaller than 0.1, we still have 99% of purity. This is much more pure ensemble than the LC because we have both quark and gluon and all these. That is why for TT bar it is less entangled. It's only matter entangled, but the level didn't reach Bell non-locality. We mentioned before, Bell equality is a more stringent condition than entanglement. Okay. So this is for the spin part, although the function is non-perturbable and slightly complicated, but it still can fit in this overall procedure. The overall procedure is same. After we have the density matrix parameterization, what we have is this here. We change the decay density matrix to the non-perturbable hybridization density matrix, and we are able to write down the final distribution in terms of pattern level polarization vector, pattern level density matrix parameters. Then we match the experiment data and reconstruct it. So this is the sports beam half particles, all the strategy, all the procedure is basically similar.
Two questions. One is, okay, I'm fine with, let's say I'm still using kinematics to project onto spin space, right, and study the spin correlations.
Yes.
Before it was decaying process, here is the hybridization process. And so how can you, it's clear there's faithful tracking using the semi-inclusive process, right? It's kinematics to spin, but I could totally have another, I will pick up a lot of my energy, right?
Yeah,
This
that is why.
be solved.
That is why the spin analyzing power, if you look at here, it is very small. It means there are a lot of dilution effect. As you said, there's a lot of dilution effect. For
Still have.
yeah, even with the dilution effect, you can still, because there is just a factor, we can, if we have a higher sensitivity, because there are so many QQ bar at Bell, we have higher sensitivity and can still see the signal.
Let me suppose I don't know this factorization and so on. And so
Yes.
I decided to study the semi-inclusive 4-pi final state. I just decided to forcibly calculate their momentum space correlation matrix between them.
That I don't think that's calculable. Yeah. Yeah.
I mean, I decided to measure.
Yes, yes.
Right? If I measure them, I can also say, oh, this matrix, have non-zero off-diagonal entries, blah blah blah. They are zero entangled state. I can make a statement.
I don't think if we don't have a quantum state to study with, I don't think you can make a statement of entanglement, because entanglement is defined as how the property of quantum state, right? Initially, what's the system we study? It's not.
So there's a 4-pi cross 4-pi space, right?
Yes.
So your formula is actually I shrink this 4-pi states into two pair of matrices of subspace and study the subspace correlation, right?
There's a difference with 4-pi are momentum space, right? They are scalars. They don't carry spin information. So what we are looking at is just a 4-pi momentum space, and here it's the QQ bar spin space. We are translating the 4-pi momentum into a spin space. It's not a subset. It's just by this assumption of factorization. If we only look at the momentum space, we need this formalization just does not work. This formalization of entanglement Bell equality only for the spin state. We need a completely different formulation.
Yeah, in principle, or ideally, I could decide to shrink them to another non-commuting space, subspace.
Yes.
Spin, but they will have non-zero relations.
Depending on your assumption, how do you factorize it? What's the state you want to study? Here, I want to study the spin half particle state. All right. So basically, that's it for the spin particle. Although there are many difficulties, but I believe this overall procedure is still looks simple.
Things used to have like more control over this and repeat something like B-factory experiment, which is like runs at epsilon 4s. Suppose now I step up in energy such that I open up threshold not only to BB bar, to open bottom states, but also like extra pines and so on, right? And then you can see how you can have the control over the spin. What happens much better.
Yes, in principle, yes. But in principle, this can also be factorized. It can be thrown all into these non-perturbative functions, like in the when it is well controlled, this spin analysis power is slightly bigger, but this all process is non-perturbative.
I have to say that this will be under control.
Yes, yeah.
Because you know the center of mass energy, you know how much space you produce.
Here it's also under control because QQ bar center mass energy is fixed at Bell, 10 GeV. Yeah, it's not LC, just Bell, E plus D minus. It's a simpler system. Okay, now after the spin state, there's another state we can reconstruct in Kleider's the flavor state. It is mostly based on my paper with Tao, Matt, and Arthur here. So actually, the quantum information of spin state is studied just in recent years, but the quantum information of flavor state are studied much more earlier. Because let's say we have a meson coming in, B meson, we don't know it is B or B bar, so it can be a superposition of B and B bar. And if a two B meson, they can also be entangled, like B bar minus B bar B, something like this. So the study of this kind of entanglement actually started much more earlier, 30, 40 years ago, and either general study or some specific properties like Bell inequality or the others. So in this talk, I'm also still focused on the tomography, because in principle, flavor can be correlated in different ways. Like we can have a plus sign, or we can minus sign, we can have differently. So the general parameterization is still this 2 qubit density matrix parameterization, 15 parameters. Okay, so this is this is the motivation we want to do. We want to know what's the density matrix at when they are produced at time 0. Okay. The difference between spin is that complementary measurement in spin space is more easier to achieve, because in the spin for spin half particles, when we expand it using the Bloch vector, this sigma is just the spin operator is embedded in our three-dimensional space. We choose different direction to measure the spin. We get a y, x, y, and z. It's complementary. Or in terms of decay, we just choose different direction to look at the decay angle. Okay, but for flavor state, it's not so easy to write down all the complementary set of measurement. We can write down one. For example, let's say we can do a tagging. B can decay to semi-leptonically either lepton or anti-lepton. Lepton is a positive one, anti-lepton negative one. Now we have one operator sigma z. We don't have the other. It's not like spin can just rotate it to the others. So we need some more non-trivial settings. For this, let me introduce some basic things, just eigenstate mass diagonalization. But I believe most of us are familiar with it. But let me use a different language, rewrite it into the density matrix. Let's say we have two mesons, M and M bar. This can be general, B bar, D bar, whatever. Okay, the Hamiltonian can be mass matrix can be written this way. And after diagonalization, the mass eigenstate is different from the flavor eigenstate. This one is flavor eigenstate. And I will consider the CP conserving limit here. The first and the second mass eigenstate basically M plus minus M bar. Very, very simple. Okay. Now if we look at the mass eigenstate and CP eigenstate in this Bloch vector parameterization, we see the Bloch vector still have some physical meanings. Especially the first one, of course, is the z direction. If BZ equal to 1, this is the first flavor eigenstate. If BZ equal to -1, this is M bar. We see this. And the more slightly different non-intuitive one is the x direction. We can see the x direction is a mass eigenstate. We write down the Bloch vector here. We can see that the first mass eigenstate is bx equal to 1. The second eigenstate is bx equal to -1. So in the following, this convention would be really important. The x direction is quite a special direction. So the difference between flavor and the mass eigenstate leads to a flavor oscillation. I believe we know this kind of oscillation, but let me rewrite this.
You're assuming degeneracy. That's why I feel like
no, not degeneracy. There is a delta M. Like here, the first mass eigenstate, second mass eigenstate. I'm assuming CP conserving. I'm assuming first one is CP even, second one is CP odd. Just CP eigenstate are mass eigenstate. This is the assumption.
So P and Q are not 1 or √2 for you.
It is 1 over √2.
That's the maximum mixed state.
Yes, that is.
Yeah, that's why x direction can be that pressure.
Yes.
P and Q are not 1 or √2, x direction does not go along.
Yes, this is the result of CP conserving. If CP is conserving, you can see from here, the capital P and Q are same. So this one is mass eigenstate. So mass eigenstate equal to CP eigenstate. So this one is CP eigenstate clearly. So this one is mass eigenstate. These two are equal is a condition of CP conserving.
But the mass is a split.
Yes, it is split.
Did you have off diagonal, please?
Here M1 does not equal to M2. Yeah, this would be important in the later part. And decay width is also split. Okay, let me rewrite again. Let me rewrite this standard flavor oscillation in terms of the Bloch vector parameterization. Let's for simplicity here, I just assume that decay width lifetime is long enough. If we have a density matrix at time 0, we write down its evolution. We see that in the Schrodinger picture, the density matrix evolution looks like this.
This formalism was known, right?
Yes, it was known.
Neutrino physics, like they use it all the time.
Yes, exactly. It is known.
Yes.
Yes. This is just the introduction part, and because this part will be important in later reconstruction. Okay, so we see that the Bloch vector is a precession around the x direction. Looks like this. It is slightly more interesting if we locate in the Heisenberg picture, because we are trying to find a complementary set of measurement. So in the Heisenberg picture, the spin operator is a precession around the x direction. Previously, we said we have one spin operator sigma z. No, sorry, not a spin operator, Pauli operator. The Pauli operator, we have one Pauli operator sigma z, this one. Now, at a different time, if we choose the same operator at different time, this can give us the y direction information. So we are already one step forward the complementary set of measurements. So let's for in reality, how do we measure this Pauli operator? This is simple from decay asymmetry, because the meson state can decay to some flavor eigenstate. I say the flavor eigenstate means that it's the final state is not a conjugate of its own, like this hard particle. So B decay to this positive charge, B bar decay to its negative charge one. So by looking at the number of positive charge one minus number of negative charge one, this is basically the expectation value of sigma z, and this is sigma z and the function of Bloch vector. Okay, and in turn.
You assume the CP eigenstate coincides with mass eigenstate.
Yes, that's the CP conversion.
That's the special.
Yes. Yeah, I will show you the CP. I will show you the CP variation parameter later. Yeah, it's very small. It's only in the mixing part. There are additional CP variation, maybe big, but in here it's only this part. Yeah. Okay. Now we say that once we measure this decay asymmetry at a different time, we can extract y and z components in the Bloch vector space. That is what we can do, or we can just do an overall fitting of the time-dependent distribution. As we write down the distribution, we can see we have both Bloch vector dependent of y and z components of the meson state when it is produced. So in reality, of course, there are some slightly damped exponential factors slightly damped oscillation, but we can just include it in the fitting. Okay.
This is why you do B meson.
Yes. Yes. K is also fine. K decay very quickly, but the decay width is it can still oscillate like a half period, right. Not a complete period, but a half. That is enough for us to extract.
That would be enough.
Yeah, that is enough. I will show the sensitivity later. Yeah. Okay, now we have y and z. The last piece is x component, because we want a complementary set. We want a whole tomography. So another decay channel of meson is CP eigenstate. The final state can be its own conjugate. Here I will use the F plus and minus to denote a CP even or CP odd final state, like this kind of final state. So it has two. This kind of decay has two effects. The first effect is that this kind of decay will lead to a lifetime difference between M1 to two mass eigenstate. Because let's assume that there's only CP even final state, then only M1 can decay to it, M2 cannot decay to it, so M1 has a larger decay width. So that's quite simple. Another effect is that this has a sensitivity on the X component, because if the meson decay to the positive CP eigenstate, then it's like firstly we project it to this M1, then it's a normal decay rate, and this projection probability is the Bloch vector along the x direction. So now with this, we basically achieve a complementary set. We can think about to combine different channels, semi-electronic channel and this kind of channel to reconstruct it. But in reality, it is slightly even simpler because only semi-electronic channel itself is enough. Let's use a toy model here. Toy model, let's consider there are two types of decay channel. Meson can decay to CP even one, or it can decay to flavor one, semi-electronic F or S bar. If the Bx is 1, it means that this meson is a CP even eigenstate. It can decay to both. So the total number decay to semi-electronically is slightly lower. This is total number semi-electronically. If the block vector Bx equal to -1, it's another mass eigenstate. It's a CP odd mass eigenstate. Then it cannot decay to this one. So everything will decay to semi-electronically. It will be this red line. So if we look at the overall number of events that decay semi-electronically, we are also able to reconstruct these components. We don't need to combine different channels. But although we only look at this semi-electronic, the extraction relies on the existence of this decay. Because here you can see there we have a delta gamma here. The extraction completely rely on the lifetime difference between two mass eigenstates. If the meson don't decay to this here, then we cannot extract it anyway. So although we don't use it, but we rely on existence. So now I think we can summarize. We finally achieve a complementary set of measurement for the flavor state. There are two observables we are going to use, all time-dependent observables. First one is the decay asymmetry, positive charge one minus negative charge one. Second one is the overall rate. The first one gives us this x and y and z directions. These two rely heavily on the oscillation. It relies on the delta m. And another one, this overall rate can reconstruct this x component. This one relies heavily on this delta gamma. So ideally, we will need both delta m and delta gamma comparable in the lifetime. Okay. Although I spend much time on the one meson, but for meson pair, the generalization is quite straightforward because we can perform these two observables on each side of the meson. For the first meson, we measure these two. For the second meson, we also measure these two. Then we have the correlation. We have 4 observables. We say the first one, for example, the total number event of both decay semi-electronically. The second one is we measure the symmetry on both sides. The other two is the asymmetry on each side on condition that the other side also decays semi-electronically. So the correlation of the two are 4. And
corresponds to the mass eigenstate.
yes.
And Z corresponds to
Flavor eigenstate. Z and Y oscillate each other. Z and Y oscillate into each other. At a different time, maybe Z become a flavor eigenstate, the Y become another flavor eigenstate.
Oh, the flavor eigenstate is changing as time.
Yes, that's a flavor oscillation. Yeah, that's flavor oscillation. Okay, just for fun, I write down the whole formula. You want to see it? There are 15 parameters we can reconstruct it. Basically, the logic is the same with the 1 qubit. The sensitivity of YZ depends on delta M, sensitivity of X depends on delta gamma. And here we also include the CP variation effect in the oscillation. And for CP bar system and KK bar system, we consider it's roughly 10 to the minus 3, 10 to the minus 5, so we just neglect it. Okay, now I think I can show some numerical result. The first one is what have been studied all the time, the simplest singlet field state. If we use block vector parameterization, the flavor correlation matrix is just identity minus identity. Okay, we want to show that for whatever initial state we can reconstruct it. For example, we can add some mixture, complete mixture. Let's assume there are some decoherence effect or whatever we don't know, give us this completely identity. Then we choose some coefficient kappa, we fit it, and we see that the fitted uncertainty of the parameters does not depend on the initial state much. So this procedure is mostly depends on the intrinsic property of the system. No matter initially how it is produced, we can all reconstruct it pretty well. For BSBS bar, we see that there is interesting thing that we see that for Y and Z component, they can be constructed. If we look at the uncertainty, they basically have the same uncertainty. They can be reconstructed equally well. This is because for this one, delta M is quite big. They already oscillate a lot after the decay. So Y and Z component completely oscillate each other. They basically are the same. However, for Y component, it's slightly harder. We see there the one order magnitude bigger uncertainty, especially for this correlation matrix CX1. This uncertainty is quite big. This is because the decay lifetime difference between two BB bar is like 10%. So we have a one order of magnitude suppression. Okay. For K long K short, we don't have this effect. All these uncertainties for different entries are roughly same order of magnitude. This is because the delta M, of course, is big. The delta gamma is also maximum. Their decay lifetime is maximum. We can extract the mass state information very, very well. Also, although it decays very quickly, it still can oscillate like about half period. Y and Z already oscillate each other. We can still have some sensitivity on the Y and Z component. So everything is basically same order. So with the complete density matrix, 15 parameter parameterization, we are able to reconstruct and measure any kind of quantum information. Here I list some examples. Like a concurrence Bell example is what we showed before, and some others. Here I just want to mention that for Bell inequality, this can be measured without the full density matrix. This is similar as what we did before for the QQ bar pair. That is why this one is already measured quite 20 years ago in other experiments, because in only part of the density matrix information is enough. But for some other quantum information observable, you may need the complete information. Okay, let me summarize. Let me use one sentence to summarize the topic. As we think the high energy colliders are quantum information laboratories, we have many different quantum states produced, and we can study its probability. Of course, firstly, it serves our fundamental interest, and also it has some inspiration on quantum information science or high energy theory. For both, for quantum information science, we have rich information, and especially we have large number of events and sometimes a good precision. For high energy theory, we have some new methods, new techniques, and but the point is that the quantum tomography can tell us the most complete underlying physics in this framework, in the framework of quantum mechanics and QFT, of course. So as long as we can do the tomography, this is the most complete picture we can see, and we have the most comprehensive understanding for either high energy theory or quantum information. So here I introduce two approaches. I mostly introduce the later part. There are two, in collider physics, there are two ways to reconstruct the state, either from the production side, either from the decay, fluctuation, oscillation side. If we can do both, it would be a good complementary comparison. But if we can only do one, like the labor oscillation, we don't know how it is produced. We can only look at the other part. That is also interesting because it can have a good reference for future development on the theory part. Okay, thank you.
Sorry, I was late, but the answer to post the speaker. Any further questions for Kun?
Yes, so again, this B meson oscillation, what did you learn that you didn't know?
Yes, this is
Sorry.
this is a case. So if we only look at this resonance, then BB bar, of course, it's because it's a charge order. Of course, it will look like this. We don't learn anything more. But if we increase the energy a lot, not a lot, a little bit, there's some additional radiation. We don't know the production mechanism. Then we don't know what the flavor state it is. But we are able to measure it now. We are able to know how the flavor state it is, and it can be a reference of future calculation.
So what is this flavor state then, if you measure it? I mean, is it some?
For example, here it could be plus minus or some other mixture, like some decoherence factor, a mixture of decoherence factor.
But you have evidence that there's something else going on there. That's
Uh,
what I'm saying.
We know something else is going on because if we go to higher energy, like from 10 GeV, we go to higher energy. There's a high energy phases. They are complete. They are inclusive process, BB bar and anything. In that case, usually we know this completely washed out, diluted. There's no correlation. But now it's 100% correlation. So from here, from the low energy to high energy, definitely it is changing. It cannot suddenly jump to no correlation.
Have you tried to see if you can learn anything about B sub S? Because the B sub S, like all what we know more or less comes from the LHC and neutron, but
Yes.
Bell had a run above the B sub S bar threshold, and it's not entangled the same way as B0 bar. You know, it keeps on for replicates. So.
Yes, we have.
So, is there anything to extract?
Yes, yes. We have estimated the B sub S at the LC. It's about slightly lower. It's about
LHC, at about 2, where you could raise the energy a little bit, and you are above the B sub S threshold, bar threshold.
yes. So the point is the reconstruction depends on number of events. As long as there are sufficient number of events, we can reconstruct the complete data very well. So we know whether it is different from original CP order state, CCC order state. As long as we have enough statistics, we can do this.
So in some sense, they have a basis to map the observables onto, and but all the rest is I have experiments I map onto these coefficients. Whether this coefficient maps to what theory is actually lacking, because some of the things are not calculable. But if they measure those coefficients, maybe future theorists will be able to try to calculate the result. I think that's there's enough predictive physics involved. Just as a Maxime example or Kun's example, if I'm producing that slide off the resonance, right, above threshold. Actually, I don't know what's the state I begin with. That's that. We are allowed to prove them.
Yeah, this is the most complete parameterization within quantum mechanics framework. So as long as we have that, this can be applied for any experiment.
And then the series job to calculate those coefficients.
Yes,
and
yeah.
discover whether.
Yeah, that job is difficult.
Any other questions or comments?
The whole point is to reconstruct this
Yes.
two-particle system.
Yes, two-particle and spin and the qubit system.
So it's not very interesting.
More particle system is similar, like we add additional one. So I introduced the one particle system, right? So the more particle system reconstruction is like just a direct product of one particle system. We measure the same observable on all the others. Then their correlation, all their correlation function.
Sounds like one should generalize the system. Say I have endpoint correlation functions.
Yeah, that is that is the
That's-
endpoint. Yeah, this is a 2 point. If you have 3 particles, you have a three correlation function.
But for instance, it would be useless to neutrino, so we know everything about the production.
Neutrino will be 3 levels.
Yeah, neutrino is a 3 for that's we can let's say we approximate to a 2 level for simplicity. Yeah. Neutrino is firstly so only one particle. It's not correlation with the others. It's just itself is oscillating. Of course, we can reconstruct it. In principle, we can also use this approach to, let's say, just to confirm the production indeed is in this state. You can measure it and confirm it, just for consistency check.
If we would have some sort of neutrino pair production, and we could follow it on the basis.
That even
I can control the carbon leptons.
that even is too rare.
Ions actually, our neutrino experiments from ion decay, that's also. In principle, if I detect a muon, I'm doing this in temperature.
Yeah, I actually asked some neutrino physicists. They just tell me you will never see 2 neutrinos together. They just
We don't need to, right? Lifetime, charge lifetime is from higher, is entangled with this neutrino.
Yes. But that's slightly trivial because it's
Yes,
only
there
left
is
handed.
this example of an A64, right, where they have the beam of the K plus particle, and they have measured at some point, I don't know, but you measure the muon coming from the decay of this kaon and the conversion of the neutrino into a muon at the distance, right? I mean, usually we measure the neutrinos without association with the parent sort of decay. Here, they saw the coincidence. I don't know. So that could be something. That's the starting point for any kind of measurement.
Yeah.
Okay, very good. Let's thank the speaker again.
Thank you.
I would like a dinner with the speaker at around 5:30. If you are interested in joining, just let me know or pay around the speaker. Thank you.
So now we finish some over group or